turning the volume up. Good morning, folks. Coming to you very soon, starting the events. Here we go. Start this lecture very soon, so let's get my notes in order. I think I'm live on streams. I think I'm live on everything else. There's a few people. There's someone watching me on YouTube. At least one person's on YouTube. Not sure. We're going to have a huge take up this morning. The time is not ideal. But that is part of life when we that's part of life when we've got a long weekend. All right. Good morning, everybody. I'm going to start my recording. Good morning, folks. Ready for week 4 in COMP2300/6300. Thank you for joining me. There's a few people joining me live. I know that many more people will catch up later on Echo 360, YouTube, or Twitch. So I'm not terribly worried about having the biggest live audience this morning. Obviously, this lecture is not at the normal time. It's Tuesday, 9 o'clock in the morning, which is not quite right for our lectures, but this is because Monday was a public holiday here in Canberra. And we'll have the same or a similar procedure later days when we have public holidays. I think we have at least one more public holiday which affects us this semester, maybe 2. I think just 1. This is going to be a busy week for everyone. I think that there are folks in the lab right now working their little fingers off, typing in lab solutions, trying to work out lab 4, which is related to blinking an LED on and off on your microbit. That's a big challenge and involves a lot of learning, so I hope people are ready for a really engaging and fun but challenging lab this week. The quiz is out. The lab pack deadline has passed, so I'm looking forward to seeing how everyone did with the lab tasks over the last 3 weeks. You've got an assessment task next week related to assignment 1, and assignment 1 is now out. I'm just listing things off the top of my head, but what you should really be doing is if you have any questions about how the assessment for COMP2300 is working, go onto the website, go into the assessment sections, have a look at the assessment scheme, click on all of these links, make sure you know what they are, and make sure that you know when the due dates are. I know that a lot of people have been engaging with the quiz already, which is wonderful. It's a really wonderful learning tool to get in there and practice things, understand how to do the questions, challenge yourself to do it without immediately looking up the answer, but you know, you get as many attempts as you want, so the help is there and the feedback is there to help you find the right answer if you can't quite work it out initially. Now today, and this week, we are starting to work on this topic, control flow. So we've had 3 weeks of looking at what I would call the basics of assembly programming, which has basically been limited to working with one instruction at a time. Looking at one instruction, understanding what it does, having that understanding about how it encodes into machine programming, machine language, into the ones and zeros, where things are in memory, what these instructions do, and how you can do certain arithmetic operations, certain memory operations in one instruction. Now we are talking about a program, a list of instructions. So at the high level, I need you to think over the next 3 weeks, we're moving from single instructions at a time to many instructions that make up a program. Now, as you found out in your Pokemon lab, week 3, the tools that you've got right now are very limited for doing things you would normally like to do in a program. It's difficult to choose which instruction to run next based on a certain value you've got. You might be in a certain situation, you want to do this. If you're in a different situation, you want to do that. This is totally normal. We do this all the time in high-level programming. But how do we do it in assembly? And this is what we're going to be working on today. You might also have been thinking about how you can have a sub-program, a list of instructions that you go to and that delivers you right back where you started, as if you were calling a function in your program. And that's what we're going to do next week. So you can see that we've made this shift now to the structure of longer programs. Structured programming. I think you might have even taken a whole course last semester, or many of you will have taken it last semester, called structured programming. I know there are some people who are doing it at the same time as COMP2300, 6300. So this idea of structured programming is what are the formal way, or what it's about is finding the formal ways and the accepted ways and the useful ways that we can add structure in between individual lines of code, structure that copes with the whole program, that help us accomplish these tasks, doing the right thing at the right time in the right circumstance, and having reusable bits of code that can be used in many situations. So today and for the rest of this week, we're looking at the first half of that equation, doing the right thing at the right time. How do you get your program to do the right thing at the right time? And how do you get it to do the things over and over again? Because that's one of the key things which makes computers useful, the ability to do one thing over and over again very quickly. Control flow. So this is today's outline. Conditionals, loops, some more conditionals. So we get a lot of, well, a number of different things. We'll see how far we get this morning, and we'll pick it up again on Thursday with that. Conditional execution. So I just talked about this slide really. How do we organize our programs? How do we take single lines of code and turn them into sequences of multiple lines? These are what we would call the elements of structural programming. The elements of structural programming. And I guess I would just, off the top of my head, say the elements of structured programming are this. Conditional execution. That means your program can run some things under some circumstances and other things under some other circumstances. We talked a little bit about condition codes on the branch instruction last week, but we're going to talk in more depth about that today. How do you make your program do one thing sometimes and another thing other times? Another one is iteration. That's loops. How do you get your programs to run something over and over again? You've probably seen a few loops in your programs already, like the main function, which sort of has a B main going back to the top. That's a very simple loop. But we might want to have loops that we have more control over. And how does this stuff, or the final one is functions, which we're going to talk about next week. But we're going to talk today about how these conditionals and these loops translate into assembly programming language. Lol. My tutors are sending me some amusing comments. Nobody here. Just making sure I know where I am. Cool, we do have a few people watching. Thank you so much for joining me live this morning. So, control flow is about conditional execution. This is the first of those elements of structured programming, control flow, which is that you think of your program like a river or a sequence of instructions flowing by, and you're choosing which instructions to run at certain times. Which ones are important, which ones are not important. Well, not important, which ones are the ones to do. Now, first of all, let's look at these two words, right? Yeah, conditional execution. So let's just home in on the conditional part to start with. Whoops. And then look at the execution part. Here's some conditional expressions. X less than 13. Is it true? Is it not? We don't know unless we know what X is. X is the same as 4. X not equal to minus 3 and Y greater than X. So now it's a condition with two variables. Length of a list is less than 128. So all of these expressions evaluate to some kind of Boolean or truth value, true or false, depending on the value of the variables. So we don't know which one of these it's going to be until we know what X is, and we know what Y is, and we know what list is. And this is where I think a few folks in the questions I've been receiving have been getting a little bit unstuck so far in assembly programming, because sometimes people have been saying, well, why don't we encode everything as immediate values and we'll know the value already? Well, that's true. You'll know the value of a program, if you know the value of x and y and list when you're compiling your program or when you're writing it on the screen, then it's quite easy to design your programs. In fact, you don't really need conditional execution. All of your values are constants. But if you don't know what x is and you don't know what y is until you run your program, you only know those things during the program, so your microbit is going to have to make decisions based on these conditional expressions. You can't do it for your microbit. Your microbit has to do it by itself. So, a little bit of a quiz, and we'll see if anyone in the chat replies. How might you express these things in assembly? Greater than, equals, not equals, less than or equals to. And these are things that you will have learned in your other programming courses. These operators, binary operators that output a Boolean value. You know that you can't write these things in assembly, right? You can't use these different operators. Is anyone going to jump in and tell me? I might jump over here to the resources, because the first thing when you're worried about how something works in assembly, the first thing to do is to have a look at your cheat sheet, ARM assembly cheat sheet. And I think you'll notice that we've got these condition codes: equal, not equal, minus negative, plus positive, overflow set, overflow clear, unsigned higher, unsigned lower or the same, signed greater or equal, signed less than, signed greater, signed less than or equal to. So these condition codes are what's going to allow us to express the concepts on this slide. But the thing with the condition codes is that they rely on being the next instruction down, or you're adding a condition to a later instruction in your program. So let's just annotate this slide with what condition codes will be useful. This will be GT, greater than, equals will be EQ, and not equals will be NE, and less than or equal to be I've forgotten, less than LE. See, even I need the cheat sheet. It's useful for lecturers and for students. Now, one thing that's important is that these two, they only rely on the Z flag, which is fine for now. GT and LE are a little bit more complicated because they work for signed numbers. N equals 0 and N equals V. So greater than has to make sure that Z equals 0, so the two numbers are not equal when you've compared them. Usually we use all of these condition codes by doing something like subs R1, R2, and this is going to run in the background R1 minus R2 and set the flags. We actually have a special instruction called CMP, which runs R1 minus R2, sets flags, but doesn't do anything with the output. So it's only a comparison test to run on those two registers. So CMP will be the instruction you run, and then you can use these condition codes in the way that you would expect. So the next instruction might be a branch, and you'll use branch greater than, and it'll take that branch if R1 minus R2, if R1 in fact is greater than R2. So, we've got this big list here of all of these condition codes, and some of them are quite clear how they work, and some of them are not so clear how they work, like these tricky ones that involve overflow are a little bit tricky to get your head around. We might go into a little bit more detail on Thursday about how those things work if we've got time. Or if someone has a question on Piazza, we'll talk about it there. So here's an example. If x is the the same number as minus 24, x equals minus 24. How do we write that in assembly? Well, we do this. Assume x is in R0. We can do an operation which sets flags, adds R1, R0, 24, and then BEQ. Then there's a label here then. So, of course, if you're writing this in something like Java, if x equals negative 24, the very next block of code you have would be the block called then. This is the then part, and then there'd be an else part after that. But in assembly, you have to make your blocks yourself. You have to use labels to define them. So in words, this is saying if x is negative 24, then adding it to positive 24 is going to result in 0, which will set the Z flag, and then that will mean that BEQ is executed and we go to the then label. Another way of writing this without the adds would be CMP R0, negative 24. I wonder if that works as an immediate, I don't know. BEQ then. So this one is going to calculate R0 minus 24. So it's R0 plus 24. It's doing the same thing. Another example, suppose x is greater than 10. Well, that's our, if x is greater than 10, that's the condition we want to run. Now if x happens to be in R0, we can do a subs, R1, R0, 10, and then use the BGT, the greater than condition code, to go to the then. Same idea, if x minus 10 is in the signed respect greater than 0, then branch to the then. So you can see that in assembly, we have to take this bit, which is a kind of test, and we have to run that on its own line, its own instruction. And then we have to respond to the data that the test has given. So we do the test in some sense, and then the action. Whereas in a high-level programming language, you might do that all on one line. Any alternatives here? Well, we can also use the CMP operation, just as I suggested in the earlier slide. This will test R0 minus 10, and then if R0 is greater than 10, it will follow this branch. Another one, mov R1 11. This one's a little bit odd. So what were we trying to work out? If x is greater than 10. If x greater than 10. So we put 11 into R1. Now we're comparing R0 with 11, and we're saying BGE, another alternative way of doing it. This one would be working out if that would be 10, and this is x, if 10 minus x, if 10 minus x is negative. So there's many ways of accomplishing the same thing. Someone's asked a question, CMP doesn't store any values in registers. No, the output, there's no output for that. no output, only sets flags. CMP is just a test only. That instruction exists only for this exact purpose of setting your flags and then doing some conditional execution. So, you know, I think you might feel a bit funny at this stage thinking, oh, why would we have a whole instruction just for this one thing? Conditional execution is really important. It's really, really important. It's super important. The only reason you don't think it's important is because we haven't been using it for 3 weeks and you've gotten used to a world where you don't need it. But when you need it, you really need it. You cannot write the algorithms you need to write normal computer programs if you don't have conditional execution. It's absolutely required. So we have at least CMP. That's one test instruction. Where's my other one? Logic and tests. There's CMP. There's this one. That's compare negative. Instead of running Rn minus Rm, it runs Rn plus Rm. There's this one, TST, which is testing if a certain bit is set in one of your registers. And TEQ, which is testing if a certain bit is equal. One certain or any number of bits is equal between two registers if they're equal at a bit level. And you can use those with immediates as well. So there's 4 of these testing instructions. At least one of these is wrong. That's not right. It should be exclusive OR. So it's sort of bitwise tests and the arithmetic tests. We tend to use the arithmetic tests more often, the bitwise tests not so much. So I guess we had this point here. The point here was we've got this concept in high-level programming, if x greater than 10. Okay, that seems fair enough. It seems fairly clear. But as it turns out, there's lots of ways of expressing this in assembly because you're kind of building the mechanics of if then else on your own. You're not using, you don't have a high-level expression to help you do this. So the question is, are there other ways of doing this and which is the best? And what we're going to do for the next few slides is work out a best if design that you can use as a template for your programs. So you need to know when you're doing conditional expressions in assembly, you need to know what flags the different condition codes are paying attention to, what the condition codes mean and what the flags mean, how to translate the variable expressions that you might be used to in a high-level programming language into assembly instructions. These things can be a little bit challenging, but you will get the hang of it and you will need to practice. So now let's just have a look in a high-level way. Here's some examples of different ways of writing an if-then-else statement. If register 1 equals register 2, then register 3 is 1, else register 3 is 0. That's pretty typical. You've probably seen this in Java or C. Here's another one down there. Here, another typical one. If register 1 is the same as register 2, colon, register 3 equals 1, else, colon, register 3 equals 0. You might have seen that one too, particularly if you've done COMP2300, because that's Python. There's 2 others here, if then else statements, which are a little bit more compact, just one line at a time. You might not have seen these ones. This one down here, register 3 equals register 1 equals register 2, question mark 1, colon 0. That one is a little bit perplexing, isn't it? This one is actually C. It works in, there's many languages where you have something like this, but it's called often called the ternary operator. That's the condition. That's a question mark, that's the then, and this is the else. So it's a kind of one-liner for doing an if then else. And again, here's another one-liner, register 3 defined to be if register 1 equals register 2, then 1 else 0. And I believe that's our goal. So many different ways, or a couple of different ways of writing the same thing. If something, then do something, else do something else. So what's the commonalities here? I'm going to make another different type of color here. The commonalities here is we've got this bit. Everybody's got this bit. That's going to be, we can call that a Boolean expression. Something equals something, it evaluates to a Boolean outcome. Boolean expression. And we've got an operator which is going to give us a bool. That's going to give us a bool as the output. Bool, bool. Then we've got a then part. Then. And we've got an else part. Else. I need more thens. There's the then, there's the else, there's the then, there's the else, there's the then, there's the else. So to do an if then else, we need to have some expression that we're using as a test that evaluates to a Boolean value. Then some code which is executed in the then case, and some code which is executed in the else case. And I'm sure that you know this from your previous subjects, but if register 1 is not equal to register 2, we run this one, not equal. And if they are the same, we run this one, equal. Do we ever run the first one and the second one together? No. There's no way for that to happen in this construction. We can never set register 3 to be 1, then register 3 to be 0 at the same time, because this expression up here is either true or false. It's only got two options. In the true case, we run the then code. In the false case, we run the else code. We never run both the then and the else code. There's no other way that this can happen. This may seem stupid that I'm telling you this because it's very basic knowledge from other coding courses, but it's very important to have a very strong mental model about how if then else works, so that when you write it in assembly, you can do it without making mistakes that mean that accidentally we're running all of the things. And I'll show you how we can make those mistakes in a minute. But let's just go through again what I said. All of these different if then else statements have an expression, that's in the if part, a Boolean condition, some code for true, and some code for false. Let's look in assembly. So we've got to do this in assembly. We've done this a bit already, we'll do it a bit more. Check the condition, that's set some flags. Do some operation which sets flags. Now the second step is we have a conditional branch to the instructions that run the then part. That should be the then. No, that should be then. Number 3, we've got to have some else instructions which get executed if the conditional branch isn't taken. So we already know how to do conditional branching. That's the BEQ, B, GT, BLE, etc. And then now we just have to set up our code so that we have some then instructions, some else instructions, and our test. That should be pretty easy, right? Let's do it. Here's a basic layout. A basic layout for this idea. If then else, but with labels but no code yet. So we've got a label here at the top that's our entry point. We don't really need to have that. That's just good to have it here in this code just to be clear where the if part is. So we run some operation or some instruction that sets flags. Some instruction, it could be comp. I would suggest using these ones that don't store a value. Comp, CMN, TST, and TEQ. Then we've got a branch, a conditional branch to the then part. We've got some instructions for the then. And then we've got an else label and some instructions there, and then the rest of the program. Seems good to me so far. Any thoughts about what might be anything problematic here? Now that I look at it closely, maybe I'm starting to see a few problems with my assumptions about how if then else works compared with this assembly program. There's a few problems with this. I don't know if I've got enough people in there. I'm just going to see if there's people watching. I know I've got at least 6 people watching, so I'm expecting someone to come up with some problems. Anybody got some problems with this one? Wow, no one's watching it on streams. I don't even know why I bother with streams these days. It's not a very useful, not a very useful service. Julian's going to log in. He's one of my tutors, and a very, very good tutor he is too, logging in to answer my questions. Well, let's look at a few problems with this one. I think I've forgotten some of the problems. I know one obvious one. One obvious one is that if we take the then branch, we end up here. We're going to run our instructions. Then we're going to end up here. We're going to run these instructions too. So if the condition is true, we're going to end up running then and else, which is a no-no. Ba-bow. No-no. I've got a toddler who's just learned to say no, which is pretty funny. She goes and does something she's not supposed to do and goes, no, no. So maybe if you accidentally run then and else together, you can say no, no, because it's not allowed. You can't run then and else together. Where would we be if we could run then and else together? But this just goes to show that it's very easy in assembly to get into a situation where you think you're doing the right thing, but your program is actually not working the way that you want it to work. This is what I meant about the mental model of if then else. You need to have a very strong idea about what exactly if then else is doing so that you can implement it in assembly. Then you need to have a strong mental model of the assembly program about what that's doing, and you need to compare these two models and see that they work together. By mental model, I mean that you need to understand in your brain how the program is working. You need to be able to sort of step through it in your mind's CPU. So, that's a problem. What other problems could there be? I don't know. There are a few. I'm sure there were more problems than just that one. I can't remember what they were. We might find out some more problems later. I guess one thing I could leave you with is a question about whether we really need all of these labels. Are some of these labels absolutely necessary, or are some of them not so necessary? We definitely need to have a B rest of program there. We don't need to have a B rest of program down here. And we need to have some way of branching to the else, because we're never going to get to the else if we take that branch. I guess this is the second problem. The first problem is if you take the then, you will go down through the else. That's the then problem. Then the second problem is if you don't take the then, you end up taking the then anyway. That's true. Also, false will also take the then because there's no branch taking us anywhere else. So we need to do something to make sure that we don't accidentally run the then code in the else case, and we don't actually run the else case in the then case. So this code, in fact, it looks like if then else, but it's completely broken. It's doing none of what we want it to do. There's no situation in which it works. So here's a better one. Here's a better one. We set the flags, so far so good. We do our conditional branch to the then. Then we run our instructions there. At the end of the then, we go to the exit of the label for that, for the if then else clause, rest of program, so far so good. If the condition is not true, we end up at this line, then we branch to the else, run those instructions, and then we move on to the rest of the program. No problem at all. This one will work. This will do what we expect. Oh, did anyone ask a question? We don't need it if. Yeah. We don't need the if label, but I guess I just have that label there as a title so we know what the what our code should be doing. You can have as many labels in your code as you want. You don't have to use them all. Some of them might just be good as exactly what they say, a label, so that you know what a bit of code is supposed to be doing. So here is one that's a little tiny bit more efficient. And in fact, it becomes a bit efficient when you switch around the then and the else. The problem here was that we needed two branch instructions, but we only actually need one. We only need the then because we can put the else first. So if we set our flags BC to then, we put the then second. If the condition is true, we run the then, we drop through to the rest of the program. So that's great. If the condition is false, we drop straight through to the else, which is the correct place to drop through to, run our instructions, take that branch, and go to the rest of the program. So this one saves us one branch instruction, basically. I guess if this doesn't work for you, no big deal. You can just have two branch instructions. You're only losing one CPU cycle, or it's not one, it's a few actually, to run a branch instruction, because it has to reset the fetch, decode, execute cycle. You know, it's always fetching one instruction ahead, so it takes a few steps to do a branch more than your typical arithmetic operations. But so we can save that instruction there and the memory it would take to store it. And the cost is we have to have if else then instead of if then else. So maybe we should call them if else thens. That might be a better way to put it, a more efficient way. Here's an example, an absolute value function, where we're going to turn numbers into their absolute values. So this will take x equal, or the function f of x, sorry, I'm scribbling out as if I'm on a whiteboard, but it's on a computer, it doesn't make sense. F of x equals x if x is greater than 0, and negative x if x is less than 0, greater than or equal to 0. So it's going to turn negative numbers into their positive complement. If x is in R0, x is in R0, it's our assumption. That's our entry point, or our argument here. So we're going to compare R0 with 0. What does that do? It's going to run R0 minus 0 in the background. You might think that that will that's not going to do very much, but it does actually set flags. It sets flags. R0 minus 0 is always R0, so it's not changing R0. But it will work, the comparisons will work. And the only flag we really need in this case is the negative flag, because we need to know if R0 has a negative, is a negative number or not. And the negative flag will be used by BLT, bacon, lettuce, and tomato sandwich, or branch if less than. Let's go down to my branches. Signed less is checking if the negative flag is not equal to the overflow flag. That's checking if negative is not equal to overflow. So in this case, the overflow is always going to be 0 because we're not doing any operation. And the negative flag is going to be either 1 if R0 is negative, or 0 if R0 is greater than or equal to 0. So, if R0 is negative, that will be 1. That means that 1 not equal to 0 is true, so less than is true. If this is 0, it'll be 0 not equal to 0, which is false, so we won't take that flag. So if R0 is less than 0, we will take BLT, the branch. If R0 is greater than or equal to 0, we will not take the branch. So it's working. Okay, takes a step to understand how these overflow negative flag calculations work, but you can go ahead and try a few examples to understand it. So far, we have, supposing R0 is greater than or equal to 0, we don't take the branch, we go to the else, we don't need to do anything, and all we do is branch out to the rest of the program and continue. So far, so good. If we do take the branch, that means R0 is less than 0, we're going to need to do the then part. We're going to mov R1 negative 1, and we're going to multiply R0 by negative 1. So that's going to be x equals x times negative 1, which will get us negative x. So, a good example of an absolute value calculation. When you're choosing your labels, and this might be the step where if you're doing some conditional execution, you will need to use a lot of labels, and you need to just keep track of what labels you're actually using so that you don't use them twice, because you can't use a label twice in a program. This makes things a little bit more complicated than working in a high-level programming language, because you can do the if-then-else in high-level programming without any kind of one-time use names for things. You can just do as many if-then-elses as you like. But every time you do an if-then-else in assembly, you're going to have unique label names so that your program knows where to go. Someone's just pointed out in the chat that there's possibly a better way of doing this, which would be to do sub or calculate 0 minus x, which would also work. But I think it's not going to save us any instructions, because to do that, we're going to need to, well, supposing x is in R0, we need to do sub R0, R0, but we got to get a 0 in there somewhere. So it's going to have to be in R1, mov R1, 0. That's one cycle, that's one cycle, that's one cycle, that's one cycle. We're still using 2 cycles to do it, so it's not any more efficient. Seems like it might be more efficient to do a sub than a mul, but in this case it's not. Like the mul and the sub are using the same machinery in the ALU to do it, so they possibly boil down to doing exactly the same thing. But it's in this case, we're not saving anything. The instructions that really use a lot of cycles is div. Div has a lot of stuff going on. I don't really understand how that works. For some reason, it takes heaps of cycles to do a div. Oh, where's my tutors when you need them? Why does it take so long to do a div? All the tutors teaching 2219, learning about all this stuff in how ALUs work with digital logic. We'll have to explain why divs take so long. And of course the answer will make sense because it has to be that way. Okay, ooh, yeah, there's our label name gotchas. Now, next topic, loops. Loops, looper. Loops are another one of these absolutely essential elements of structured programming. You can't run all of the algorithms you need to run if you don't have iteration in your programming language. You've probably encountered at least two different ways to do iterations in programming. One would be the functional approach, where you're doing a kind of recursive calculation. So some function might do some test function, I don't know, blah. If something happens, call func n minus 1, else return blah 0. That's your kind of functional recursive. I'm doing a really poor recursion example right there, but we will do some more recursion later when we know what a function is in assembly. And then you'll also have learned this kind of while n greater than, 100. Do some stuff, and at the end of your loop you say n equals n minus 1. So that's your typical while loop. Now, let's just draw your attention to this. In the iteration you've been doing so far, it's been just like you get a... Sorry, I do all my writing on an angle because of the angle of my tablet, but I don't know why. I could just turn my body and my tablet and I'd probably be straight, but there you go. You've got your main label, you do some stuff, and then at the end of it you got B main. Now, the difference between this loop that you've done weeks 1 to 3 and these loops, week 4 plus. The questions are coming in now. Hope no one's late for the Tuesday 10 a.m. lab. There are students in the lab right now. Hope you have me on a big screen. The difference between the week 1 to 3 loops and the week 4 plus loops is that this one will never end. This one goes on and on forever. Both of these loops, or both of these iteration strategies, will end at some point. And how do you know when they end? Conditional execution. You've got control flow here. We've got our test. We've got some kind of an if then else with a test in it. And greater than 100. And greater than 100. So we're looping while some condition is true and then stopping at some point. So these ones will stop. These will stop. Which needs conditional execution. This goes on forever. Infinity and beyond. Okay, enough drawing. While loops. We got two kinds of loops to talk about today, so I'm going to keep pushing through. We're not going to spend as much time here as the long explanation before, because they use a lot of the same parts as the if then else clauses. Just the simple comparisons, the conditional execution, conditional branching. We're just going to know exactly what a while loop is doing and exactly what a for loop is doing in order to make a good version of these in assembly. So, while loops. Here's a couple of while loops. Some of these ones make sense to me, some of them aren't in languages I really have ever used, but a good example is this classic kind of C Java while loop. While register 1 less than 100, we're going to do register 1 equals register 1 times register 1. So no matter what we do, every time we run through this loop, register 1 is going to hopefully get bigger. I suppose if we start with a number like 2, R1 equals 2 to start with, it will always get bigger. Eventually, it will be greater than 100, and at that point, we stop the loop. Here's a Python loop. While register 1 less than 100, register 1 equals register 1 to the power of 2. That's just sort of squaring it. That's what that operator does. You don't typically get that one in C for free, so we don't use it. So again, what are the common elements here? We have an expression. We have a Boolean operator. So we know these things evaluate to a bool. 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 That was only a bool. I need another oo. Bool. We have a code to run if it's true. So it's sort of a then, or it's a loop body. Loop body. And we're only running one line in this loop. It's a very simple loop. By the way, what happens if register 1 is 1, for instance? 1 defined as 1 times 1 is 1, 1 times 1 is 1. It's never going to change, so our loop will get stuck. It'll go forever. But these loops at least have the possibility of escaping. So, and we know from a while loop, I guess I'll go to the next page to go through these details. We've got our expression, we've got the Boolean condition, and we've got code inside the loop. Remember with these loops that the while loop checks the condition and then runs the loop. It doesn't run the loop, then check. So the first thing we do is check R1 less than 100. If true, run loop body. 3, go to 1. So that's our loop. First check, then run. If we come up with R1 equal to 101 as our entry point, R1 equals 101, it will fail this test, no, and go straight down to the rest of the code. It will not run this code, not running the code. So in assembly, we've got to check the condition, that is set some flags. We need to do a conditional branch to test whether to break out of the loop or to run the loop body. If branch is not taken, we're going to execute the loop body code. Then we go back to step 1. Here's some example with labels, but no code yet. Begin our while loop. We will do something that sets some flags. B something, condition into the while loop body, and then if that's not taken, this is testing the if condition. If it's not taken, we just continue on and don't run the loop body. Running the loop body, inside there, we go back to the begin while. So we 1, test, 2, run, 3, repeat. Now again, we've got the same potential little inefficiency where we've got 2 branches here. So it's not the absolute best while loop we could have, because there's surely a way to do this with one single branch. We might try that in a minute, but it will be the same trick as with the if then else code, which is that we're gonna kind of invert our test. So we do one test about whether to escape or not, rather than a test of whether to do the loop. While x not equal 5, x equals x divided by 2. So I've been lecturing for too long and my coffee's gotten cold. It's still nice. Begin while, it's just our title label. Compare R0 with 5. If they're not equal, branch if not equal, then we run the while loop body. There's the while loop body. If is equal, we go to the rest of the program, continue on. And then in the while loop body, we do our actual looping stuff. Divide x by 2, we're just dividing by 2, integer division, ASR, arithmetic shift right. So, or sign shift right. So we're going to be doing a shift right to divide by 2, which will work for positive and negative numbers, and then go back to the beginning of the while loop. So we do need this one here because we need a label to go back to. But do we really need this label? That's the question. The while loop label. Do we need that one? I don't think we do, because it could be that instead of doing this, we cut that line. The opposite of x not equal 5 is x equals 5, so we could do b eq rest of program, and then we don't actually need this label. Do you see how that works? We're testing, do the test. If it is equal, we escape the loop. The only other option is that it's not equal, so we need to run the loop body and do the loop again. So again, we're just taking advantage of the fact that these Boolean tests, they're either true or they're false. There's only two options. So we can test one option and assume that the other is the case if it's not. We don't have to do two tests every single time. So this is the opposite, it's opposite stay, opposite test to escape. To escape. Sorry for my small writing on a big board. I think the next slide does exactly the same thing. So we have our begin while, our first thing is the comparison, then we invert the conditional check, BEQ rest of program. If R0 is equal to 5, we escape the loop and move on, and continue on in the program. What do I see students doing? If I ask students to write a while loop, I see sometimes a few problems, a few mistakes. One thing is doing this bit first. No, no, no. Don't do the action first. Another thing will be forgetting this. You need to have this one. Yes, yes, yes. You do need to begin to the first part of the program. I guess sometimes people are thinking of a loop as in they run the code in the loop and then they try to work out whether they go back to the top or not. But you have to remember that a while loop always does the check first, then runs the code. And if the check fails the first time, it never runs the code. So it's wrong to run this bit first. Sometimes people write a while loop where they've put the code, the loop body first, but they've changed the looping conditions so that it still works, which gets the right answer, but it's like not a while loop. It becomes a different kind of loop. There's a different kind of loop called do while, where you've got your condition and then you've got your body first, then your while condition at the end. So that runs the loop body first, then does the while code. So if I ask you to write a while loop in any situation, please actually write a while loop. Don't write a different kind of loop that seems like it might be a while loop, because it doesn't answer the question that I'm asking you. So be careful with these things. It's important to learn them and important to practice. And I hope you will in your assignments. Things to note here, we needed to reverse the condition. The while loop had the not equal test, but we used the equality test instead. We used the CMP instruction to set flags without changing values. I pretty much always use CMP. I think I see other people doing other stuff, but I just like to do it the most straightforward, easy way for me to understand later when I've forgotten what I was trying to do. The loop body may contain lots of assembly instructions. You can put as much stuff in here as you want. It could be a whole bunch of 1,000 lines of programming. Could be inside that loop. It might take a long time to do your loops then, but not that long. Remember with this particular loop that if x is not a multiple of 5, it's not going to ever hit 0, so it will never stop. So again, it's a dangerous loop. It might end up being an infinite loop. For loops, our next kind of loop. For loops are one that, sorry, this doesn't look quite right there, does it? But the highlighting doesn't look quite right. This is the way that I guess I was first taught to do a for loop, in this Java-y C kind of way. We start with a for loop. You've got this idea of changing a counting value and doing a test on that each time, and the changes that occur for that counting value sort of are built into the structure of the loop. So the first thing we do in this loop is we set register 1 equal to 1. It's its starting value. Then we do a test, just like in the while loop, register 1 less than or equal to 100. It's true because it started at 1. Then we run the loop body. Then we do some kind of change to the counting value. There's other kinds of for loops. For register 1 in all the numbers between 1 and 100. So that's building in the test and the update and the starter value all together in one very compact statement. Do this loop body. For register 1 in range 1, 101. It's Python because range kind of gets you, it ends up being 1 less at the top part of the range, which is an annoying thing about range. Register plus equal register 1. Actually, I've always messed that up in Python about range, which is probably why I'm not very good at Python, but there you go. Similar idea. All of these examples have a test. They've got a counting variable. There's our counting variable. I'll make that in green. Counting variable is register 1, counting variable, counting variable, counting variable. There's our counting variable. It's also used in the loop body for some reason, but you don't have to use it. Sometimes the counting variable is just there just to make sure you do exactly 100 iterations of something. There's the counting variable is used in the loop. Then we've got some kind of parameters on our counting variable that tell us where it starts, where it ends, and how much is changed in between each loop iteration. And those are all done in this very compact way in these other programming languages, and in C and Java it's done in a more expansive way. Of course, in Java you can do for each loops or some kind of slightly different for constructions on list-like things, but the kind of loop we're talking about, the for loops we're talking about here, are the strictly kind of arithmetic ones based on a counting variable. So we've got an index, that was what I called the counting variable, a start value, an end value, and code inside the loop. That's the counting variable. How do we do it in assembly? We are going to check some conditions on the index variable. So check some flags, set some flags. We'll have a conditional branch to test whether to escape the loop or break out of it. If the branch was not taken, we're going to execute some code in the loop body, which could use the index variable, doesn't have to. Then we're going to increment or decrement or whatever, do something with the index variable as our almost last step, and then branch back to step 1. A few traps for young players would be not doing this step at all, or doing it in a different place that's not the very last thing you do before branching back to step 1. And similarly with the while loop, you've also got to make sure that the loop body stuff comes after your conditional branch, not before. Here's a for loop with code labels but no code, same idea. We do some setup for our index register, set some flags, do the loop body, update the loop register, and we've got our condition here for escaping the loop. In the same way as the while program, I'm using now the optimized, very efficient while method that only uses one conditional branch. So that's going to test our escape condition. Make sure that this update the index register thing happens here. That has to be there, not somewhere else. So here's an example. You'd like to add up all of the numbers less than 10. All the odd numbers, actually. So we start with our accumulating variable, for int I equals 0, I less than 10, plus I. If I is divided by 2 is, or I mod 2 is 1, that means it's odd. We do odd sum equals odd sum plus I. How are we going to test if a number is odd in assembly programming? I guess there are lots of ways of doing it, but really, if we've got a number that's, well, it's any number of binary digits, B, 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 and then there's a very last one, which is the ones column. And really all we have to do is test if the ones column is set or if it's unset. And a good way of doing that is to do and B, 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 and with 1. So if we have our R0, it might be something we're testing, R0, and R0, 1, and so that's going to test if they both have a 1 in the ones column, and if it does, then the answer will be 1, and if it doesn't, the answer will be 0. So if 1 is set, that means it's odd, the answer will be 1. If 1 is not set, so not odd, answer will be 0. What is this going to, how do we check this then? We actually are going to check the 0 flag, because the 0 flag will be set in the 0 case and unset in the 1 case. So EQ means that 0 flag is set, which will be set in the even case. EQ means even, and NE means odd. Now going back to our cheat sheet, no, boy, there must be a nicer way to do this than using the AND instruction, because that is just going to, it's going to have to put the value somewhere. But can we do this similarly to the compare instruction? In fact, we can. We've got the TST instruction. Test RN RM is just going to do RN and RM. So we can use TST instead of ANDs to test if it's odd or not. Let's do it in assembly. So far, we haven't added anything. No, we're not going to do it at all. I'm going to have to do it in my, I thought I was going to give a worked example. have to write something? Come on. Okay, here we go. I might put a worked example in that slide. Remind me if I forget to do it, because it's good to have the worked example. Get rid of all this. What was the question again? All the odd numbers less than 10. Okay, so this is going to be odd sum of R1, 0, that one's I. For exit for, what do we have to do first? We got to do our comparison check. So the first thing we do is check that I is less than 10. Compare R1, 10. And if in fact it's greater than or equal to 10, BGE, we go to exit for. I'll put a comment there. If I greater than or equal to 10, exit loop. Sorry about my, I'll just go get a bit more space over here. Okay, that's better. I got a disco board, no microbit plugged in. I'm gonna say disco board for my whole life. Thanks COMP2300. So now I've got to write my loop body. Oh, I need one more thing. I need my update to my index variable. So I've got to do add 1, 1. I equals I plus 1. That plus I is the same thing. Change the value of I. Okay, I've got my for loop, and by itself this should just work on my, I possibly have some stuff here I shouldn't have. Get rid of that. Put a not down there. Some crazy function, don't need that. Okay. Let's see if it works. We've got R0, 0. So far we're not doing anything with R0. We are going to do something with R1. Compare R1 with 10. We've done the comparison, and we know that our negative flag is 1. They're not equal. It's set the flags, so we should be able to go straight through into our loop body. It's not exiting. Good. We can add 1 to R1. Oh, I didn't go back to the top of my loop. That's my mistake. I need to add B4. Go back to top of loop. See, it's not so easy just to write these things off the top of your head, is it? I don't want to... I'll start my program again. Let's just set it running, looping over and over again. 0, 0, good. Do the comparison. We don't exit the loop. Now we add 1 to that. Go back to the top of the loop. Okay, now we can run this a few times. Just want to see that my loop is actually doing what I want. Okay, it should let me do the loop one more time. This time I get to 10. Compare R1, 10. And we should exit the loop, and it did. So the loop is working the way I want it to. Now I got to write the body. So we have to do an if then else. This has got to be if I is odd. So we don't need our we don't need a first label or anything. We just better do a calculation and a test. How do we decide to test that I would be odd? That would be doing test R1. This tests if bit 0 is set. That is I is odd. Okay, and when I just now have to think about the condition codes I want. I'm going to have my then and my else. So my else is nothing. Else my else just escapes the if test. So I actually not going to need a label for that. I can just do my test and escape. There needs to be a conditional branch. I can just escape my loop, my if it's not odd. So if bit 0 is not set, the answer will be 0. So it should be BEQ and if. Well, I might give it a just more descriptive label. Not odd. Sometimes, well, this is one of the advantages of assembly, I suppose. You get to do whatever you want, which can mean that you make life incredibly hard for yourself by doing things which are completely insane or difficult. Or, and this is the cool bit, you can make life easy for yourself by writing labels that are descriptive and giving your code a lot of structure that makes sense to you. So it makes more sense for me. Rather than calling this else, I can call it not odd as a label. So not odd, I do nothing. I just continue in my program. Okay, test if not odd, then exit if. If it is odd, then we do 0 or add 0, 0, and I. Okay, let's see if our program works the way we hope. We're starting with 0, which is an even number. So we start with 0. I'm sure I've made a mistake. It will be a miracle if I haven't made a mistake with this. So I've just not in my assembly programming brain right now, I suppose. I'm in my talking brain. Compare R1 with 10. We know that our for loop part is correct, so that's not going to go anywhere. Test R1, 1. We'll run the test, and let's keep an eye on the flags. So the 0 flag is 1. That means it's not odd. So we should be taking this branch to go down to not odd, which we do. And we increment the index back to the top of the 4. Now our index is 1. Which is odd, isn't it? So we can test if it is odd. We found that our negative flag is 0, our 0 flag is 0. That means that it is odd, so we should be adding it to the accumulator. Odd sum, so our odd sum now is 1. Keep going through the loop with 2, which is not odd. 3, which is odd. We've added 3 and 1, 4. 4 not odd, 5 is odd, 6 not odd, 7 is odd, doing the add of the odd sum, 8 not odd, 9 is odd, and 10, not odd. So what number do we have here? 25, is that right? What have we got? 1 plus 3 plus 5 plus 7 plus 9. It's 25. We got the correct answer. The for loop works. I'm just going to put this somewhere so I can put this on the slide, because I think it's nice to have a worked example in the slide. I'm actually probably going to stop in a minute. I've got a few more slides to go through, but I'll just check my chat. No one's asking any questions, so this must be completely sensible for everyone. Everyone understands how to do this little for loop. So what are the elements of this for loop? Let's just go through them again. We've got an I, that's an index. We've got a test, an expression to do a Boolean test. We've got a loop body, and the loop body is including an if-then routine. And we don't need an else in this case, so this is the else case. Else, then, else, not odd. Increment the index. Return to the top of the for loop. That's a pretty nice for loop, if I say so myself, if I may say so. Now, before we stop, I'll just mention a few other things. There's a thing called a do-while loop. Do-while. So I think I mentioned that before. The idea of the do-while is that you do your body first, and then you check the while condition at the end. So you run the body always once just to get it started. You can iterate over different kind of data structures, collections or lists or something in different programming languages. It's possible to have loops that have an early exit. You might have seen a word in your higher level programming languages called break or continue, which will kind of escape the loop early. Go and have a look at the list of all the types of looping structures available on Wikipedia. So in assembly programming, all of these loops share these basic features of an expression, a test, and some conditional branching. But what makes them distinctive is the order in which you do these different things. So the problem is that assembly language lets you as a programmer do anything you like, but you need to be confident that what you're writing actually means what you intend it to do. So you need to be very confident with these control structures in assembly. It is definitely core knowledge. It's something which is always on exams in this course. And I encourage you to use your lab times and your assignments as good opportunities to practice these techniques. Try to think about how you would accomplish something with a loop, and then do a really great loop in your assignment to show off how to do it. One of the really important ways or important uses for a loop in assembly programming is using them to iterate through a data structure. And I think you might have seen on this slide, we were having a look at iterating through some text stored in memory last week. And on Thursday, we're going to do this with a for loop, iterate through some text in assembly. So this is one of the main ways you'll use iteration, is to move through memory, move a pointer through memory slowly, and use a bit of that memory at a time for a task. So we'll get to more of that on Thursday morning. That demo, yeah. Is that really going to go here? I think I might start it again on Thursday, because I don't have much left in the, I don't have so many slides after that. We will also have a look at this IT blocks thing, IT blocks. This is where there's like a conditional code on the end of a lot of those different instructions on the cheat sheet. And I'll show you on Thursday morning how to actually use those conditional blocks or conditional codes on any assembly instruction. It's really clever, and it goes to show actually how important conditional execution is in the in assembly programming and in computer programming in general, because there's this whole kind of hack, or not a hack, it's a clever design of the ARM Cortex-M4 CPU to allow you to do very neat, short, if-then-else expressions if you just have a few instructions, and it's like built into the core parts of the CPU to do it. If I just run a program and have a look in the XPSR register, there's parts of the program status register which are entirely dedicated to doing these if-then conditions. So you use the PSR register to store a representation of an if-then-else structure, and then it allows you to do that with any instruction after that. It's super clever. We'll look on Thursday. So for now, I'm just going to skip that and go to the questions part. Questions? Because this one took 90 minutes already, and I don't want to go too far into everyone's labs. No one's jumping in with questions so far. I presume that all of this if-then-else stuff is filtering through people's minds. If you're watching me on streams or on Echo 360 later, make sure you do some practice with one of these examples. Run one of the examples from my slides, see how it works, make a modification, see if you can improve it. No one's jumping in with any questions, so I think I might say goodbye. And I will join you folks on Thursday morning. Have a great time in your labs this week. Until Thursday, catch you later.